All right, let's get ready to explore the cosmos. We're diving deep into a chapter from Professor Ramesh Dungana's book, Introduction to Astronomy.
Sounds fascinating.
He shared it with us.
Right.
So I know you're ready to go beyond just, looking up at the night sky and really grasp what's out there.
Absolutely. That's what I love about astronomy.
Yeah.
It takes us from simple stargazing to really understanding like the mechanics of the universe.
It totally does. And Professor Dungana, he kicks things off by addressing something that I bet a lot of us have wondered about at some point, the difference between astronomy and astrology.
Oh, that's a good one.
What do you think about that?
I think it's a really great place to start because the words sound so similar,
Right.
but the subjects are really worlds apart. So astronomy is really a science.
Right.
It's built on observation, data, mathematical models, that kind of thing.
Right.
Whereas astrology connects the positions of celestial objects to human affairs and personalities. So like your horoscope.
Right. So one's a systematic study.
Exactly.
That's the universe. And the other one is more about the, interpretation and symbolism.
Yeah, I think that's a good way to put it. And Professor Dungana really emphasizes that astronomy relies on the scientific method.
Okay.
Which is all about testing hypotheses, gathering evidence, and refining our understanding based on what we observe.
That makes a lot of sense.
Yeah.
Okay, so getting into the kind of the nitty-gritty of astronomy, the chapter talks about scientific notation.
Okay.
And I'll admit, it's been a while since I've had to use exponents.
Well, it's so crucial in astronomy because the distances and the numbers we're talking about are just mind-bogglingly huge.
Yeah.
Like imagine trying to write out the distance to the nearest star in miles.
Oh my gosh.
It would be insane. Scientific notation is really what makes these numbers manageable.
So instead of a string of zeros
that
would make anyone's eyes glaze over, we use powers of 10, right?
Exactly. It's like shorthand for really, really big or sometimes really, really small numbers.
Right.
Like the speed of light, for example. It's about, 186,282 miles per second.
Wow.
But in scientific notation, that becomes 1.86 times 10 to the 5th miles per second.
Much easier.
Way easier.
And Professor Dungana also mentions significant figures.
Yes.
Which always kind of seemed a bit fussy to me in school. Like, why do we
I know what you mean.
need to worry about that?
It might seem that way, but it's actually all about honesty in measurement.
Okay.
Significant figures tell us how precise our measurements are.
Oh.
And in astronomy, we're often dealing with estimates and approximations.
Right.
So using the correct number of significant figures is really important to avoid misleading levels of accuracy.
So it's about representing what we know.
Exactly.
And the right level of certainty.
Yes.
No more, no less.
And that rigor is so important for building a solid understanding of everything in the universe.
Okay, and speaking of the universe, Professor Dungana gets into its structure and what it's made of. And I have to admit, I sometimes feel overwhelmed by the sheer scale of it all.
It's definitely awe-inspiring, isn't it?
It is.
So we start with these tiny building blocks.
Okay.
Atoms forming molecules.
Yeah.
Then gas and dust clouds. And from there, it's like a cosmic construction set.
Wow.
Stars ignite, planets form, galaxies start to swirl, and gravity's kind of holding it all together.
And then these galaxies themselves, they group into clusters.
Yeah.
And superclusters.
Exactly.
It's amazing how it all fits together.
It really is. It's like a cosmic web, stretching across these unimaginable distances.
Yeah.
And this is where the concept of light years comes in.
Okay.
And Professor Dungana really wants to emphasize that a light year is not a measure of time.
Right.
But a measure of distance. It's the distance light travels in 1 year.
Okay, so if we see a star that's, let's say, 100 light years away, we're seeing light that left that star
100 years ago.
100 years ago. It's like a time machine.
It is. We're looking back in time when we observe these distant objects.
Right.
And, when you think about it, even sunlight takes about 8 minutes to reach us.
Oh, really?
So we're always seeing the sun as it was 8 minutes ago.
That's a really cool way to, visualize it.
Yeah.
Now, something that always kind of tripped me up is the relationship between angular size and distance.
Okay.
It seems so counterintuitive sometimes.
It can be. It's all about perspective.
Okay.
Think about holding your thumb up at arm's length and closing one eye.
Hey, I'm doing it.
So your thumb seems to cover a certain area, right?
It does.
Now, move your thumb farther away.
Okay.
It appears smaller, even though its actual size hasn't changed.
Right.
So its angular size, the angle it takes up in our field of vision, gets smaller the farther away it is.
Got it. So it's not just about actual size. It's about
exactly
our viewpoint and the distance.
As you point the distance.
Okay, I'm starting to get it.
Professor Dungana uses the example of the sun and the moon, which appear roughly the same size in the sky.
Right.
And that's because even though the sun is much larger than the moon, it's also much farther away.
Oh, I see.
So their angular sizes from our perspective on Earth are nearly equal.
That's a helpful way to picture it.
Yeah.
So it's not just about actual size, but
right.
about our viewpoint and the distances involved.
Exactly. And that principle applies to everything we observe in space, from planets to distant galaxies.
Wow. So it's all relative.
It really is.
In the grand scheme of the universe.
It highlights how our position in space shapes our view of the universe.
Yeah, it's like this cosmic game of perspective, you know, where distance plays a key role.
Exactly. Okay, so let's talk about planets.
Yes.
Planets.
What are they? Exactly.
Well, in the chapter, Professor Dungana explains that planets are celestial bodies that orbit a star.
Okay.
And they don't emit their own light. Instead, they reflect the light of their host star, which is what makes them visible to us.
So when we see a planet like Mars,
yes,
glowing red in the night sky, we're actually seeing reflected sunlight.
Precisely. And what's fascinating is that the planets in our solar system, they exhibit this incredible diversity in terms of their size, their composition, their atmospheric conditions.
Right. We have gas giants like Jupiter and Saturn.
Yeah.
Rocky planets like Earth and Mars. And then these ice giants like Uranus and Neptune.
Right, and it's incredible how each planet has its own unique story to tell.
Yeah.
It really speaks to the vast range of possibilities within our own cosmic neighborhood.
And as Professor Dungana points out, studying planets is a key area of research in astronomy today.
Absolutely.
As scientists seek to understand the processes that led to their formation and evolution.
And how they change over time.
It makes you wonder how many other planetary systems are out there.
Right.
Each with its own unique collection of planets.
It's a question that keeps astronomers on the edge of their seats.
For sure. Okay, so shifting gears a bit, Professor Dungana talks about the concept of light.
Okay.
And its properties, particularly electromagnetic radiation.
Right.
And I remember from my science classes that light can behave as both a wave and a particle.
Yes.
It's always been kind of mind-boggling to me.
It's one of those concepts that just revolutionized our understanding of physics.
Yeah.
So light can indeed exhibit both wave-like and particle-like behavior, depending on how we observe it.
Wow.
And this duality is fundamental to understanding how light interacts with matter and how we perceive the universe.
Okay, so when we talk about light waves, we're referring to electromagnetic radiation.
Right.
Which encompasses this wide range of wavelengths.
Exactly. From radio waves, which have the longest wavelength,
okay,
to gamma rays, which have the shortest.
Gotcha.
The electromagnetic spectrum really spans a vast range of energy levels.
And what we perceive as visible light is just a tiny sliver of this spectrum.
It's amazing, isn't it?
It's incredible to think that there's so much more to light than what our eyes can see.
Absolutely. And Professor Dungana emphasizes that by studying the different wavelengths of light emitted or absorbed by celestial objects, astronomers can gain insights into their composition, temperature, and even their motion.
It's like a cosmic fingerprint. You know,
I love that.
Revealing the hidden secrets of stars and galaxies.
That's a great analogy.
Okay, so speaking of stars, Professor Dungana introduces the concept of stellar evolution.
Right.
Which describes the life cycle of stars from their birth to their eventual demise.
It's fascinating to think that stars, like living organisms, actually go through a life cycle.
It is.
With distinct stages.
Yeah.
And it's a remarkable process that's driven by the interplay of gravity, nuclear fusion, and the balance of forces within a star.
So how does it all start?
Well, stars form from these vast clouds of gas and dust that collapse under their own gravity. And as the core of a collapsing cloud heats up, nuclear fusion ignites, which converts hydrogen into helium and releases tremendous amounts of energy.
And this energy is what makes stars shine.
Precisely. And the energy released from nuclear fusion counteracts the inward pull of gravity, creating a delicate balance that sustains a star for millions or even billions of years.
Wow, but this balance can't last forever, right?
Right, it doesn't.
What happens when a star runs out of fuel?
Well, that's where things get really interesting. The fate of a star depends largely on its initial mass.
Okay.
Massive stars burn through their fuel much faster than smaller stars.
Right.
And they end their lives in these spectacular explosions called supernovas.
Oh, wow. Supernovas. They're some of the most powerful events in the universe.
They're incredibly energetic, releasing immense amounts of light and matter into space.
And these explosions, they actually play a crucial role in the evolution of galaxies, right?
They do. They enrich the interstellar medium with heavy elements that eventually become the building blocks of new stars and planets.
So it's a cycle of death and rebirth on a cosmic scale.
It's pretty amazing.
It is. And the remnants of supernova explosions, they can take on various forms, including neutron stars and black holes.
Which are some of the most extreme objects in the universe.
Yeah, neutron stars are these incredibly dense objects.
Packed with unimaginable amounts of matter.
And black holes, they have such strong gravity that nothing, not even light, can escape their grasp.
It's mind-boggling to think about the sheer power and density of these objects.
Professor Dungana's chapter is really taking us on a whirlwind tour of the universe.
Yeah, it's a wild ride for sure.
It's incredible how much we've covered already, like from the building blocks of the universe to the life cycle of stars. Professor Dungana really packs a lot into this chapter.
He really does. And he doesn't shy away from those big questions either, you know?
Right, like those existential questions.
Yeah.
In astronomy, for instance, he talks about the concept of the expanding universe.
Oh, yeah, that's a big one.
I've heard about that, the idea that the universe isn't static.
Right.
It's constantly stretching outwards. But how do astronomers even know that that's happening?
That's a great question. It's actually based on observations of distant galaxies.
Okay.
So in the early 20th century, astronomers like Edwin Hubble, they noticed that the light from these galaxies was redshifted.
Redshifted?
Yeah, meaning that the wavelengths were stretched like towards the red end of the spectrum.
Okay.
And this redshift is, it's analogous to the Doppler effect that we experience with sound waves.
Oh, like when a siren passes by.
Exactly.
And the pitch changes as it moves away from us.
Yeah. So with light, a redshift indicates that the source of the light is moving away from the observer.
Oh.
And Hubble's observations showed that the farther away a galaxy is, the greater its redshift.
So that means?
Which suggests that the universe is expanding in all directions.
So it's not just the galaxies are moving apart within space.
Right.
But space itself is expanding.
Exactly. Space itself is expanding, carrying the galaxies along with it.
That is mind-blowing.
It is. It has profound implications for, like, how we understand the universe's origin.
Right.
And its ultimate fate.
And that leads to the Big Bang Theory.
Right.
The idea that the universe began from an incredibly hot, dense state and has been expanding and cooling ever since.
That's the prevailing cosmological model right now.
Oh, wow.
And it's actually supported by a wealth of observational evidence.
Like what?
Well, including some things like cosmic microwave background radiation.
Okay.
Which is essentially a faint afterglow of the Big Bang.
So it's like a baby picture of the universe.
It is, revealing its state just a few 100,000 years after the Big Bang.
That's incredible. It's an incredible window into the early universe.
It really is, and it's just one example of how astronomers use observations and scientific reasoning to kind of piece together this grand cosmic narrative.
This deep dive has been an amazing journey through the fundamentals of astronomy.
It has.
I feel like I've gained a whole new appreciation for the vastness and complexity of the universe.
Me too, and it all started with a single chapter from Professor Dungana's book.
It's true.
It's a testament to the power of scientific inquiry and the human drive to understand our place in the cosmos.
You know, what really strikes me is that even after all this, we've only just scratched the surface.
I know, right?
There's so much more to learn and discover about the universe.
And that's the beauty of astronomy. It's a field that's constantly evolving, with new discoveries and insights emerging all the time.
So who knows what wonders await us in the future as we continue to explore the depths of space.
Absolutely.
Well, after this deep dive, I'm definitely inspired to keep looking up at the night sky with a sense of wonder and curiosity.
That's the best takeaway.
And for our listeners, if you want to delve even deeper, why not pick up a copy of Professor Dungana's book?
I highly recommend it.
And continue this incredible journey of cosmic exploration.